we will be discussing about vapor pressure of liquid solutions, especially the vapor pressure in case of liquid in liquid solutions and solid in liquid solutions. Can you tell me what liquid solutions are? Exactly. The solutions in which solvent is liquid is called as liquid solution. So solute here can be a solid, liquid, or it can be a gas. Here, generally, the liquid solvent is volatile and the solute may be volatile or it may not be. Volatile substances are those which get easily evaporated when heated. For example, petrol, kerosene, ether, etc. On the other hand, when you heat the substances, if it do not evaporate easily, are called as non-volatile substances. For example, if you take sugar and you heat it, it will not evaporate. So, sugar is an example for non-volatile substance. Let us discuss about the vapor pressure in case of liquid in liquid solutions. Don't forget that we will be discussing only about binary solutions. So the solutions that are having only two components. We are going to study about the vapor pressure. So we need to know what this vapor pressure is. It is the pressure exerted by the vapor present above a liquid surface. For example, if you take water in a container and heat it, water will be converted into vapors and escape into atmosphere. These vapors cannot exert any pressure on the liquid because they escape into atmosphere. Now, if we close the container with a lid, the vapors cannot escape and they will exert a pressure on the liquid present below them. This pressure exerted by the vapors is what we call as vapor pressure. I told you that the molecules undergo vaporization. Can you tell me which molecules are undergoing vaporization? It is the surface molecules that are undergoing evaporation because they have high energy and are bound to less number of surrounding molecules compared to those molecules of water which are present inside. So, always remember, it is the surface molecules that will be vaporized in any liquid. As you continue heating, the molecules from interior of the liquid will gain energy and move to the surface. And these molecules undergo vaporization. And this process continues. Now, let us consider a binary solution of two volatile liquids in a closed vessel. Why it is volatile liquids? Because only volatile liquids will be converted into vapor form. Only when the liquid is converted into vapor form, it will exert vapor pressure, right? Let us denote the two components as 1 and 2. Since the components are volatile, when heated, they evaporate. When heated, these liquids will be converted into vapor and vapors condensed to form liquid again. So, there is a dynamic equilibrium between the vapor phase as well as the liquid phase. Let us consider the total vapor pressure at equilibrium stage as P total and P1, P2 be the partial vapor pressures of two components 1 and 2 respectively. These partial pressures P1 and P2 are related to the mole fractions chi1 and chi2 of the two components 1 and 2 respectively. How they are related? The relationship is given by French chemist F.M. Raoult. The relationship is known as Raoult's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. So, for component 1, P1 is directly proportional to chi1, By removing the proportionality symbol, we can introduce a constant and we can write the expression as P1 is equal to P1 naught into Chi1, where P1 naught is the vapor pressure of pure component 1 at the same temperature. Similarly, for component 2, we can write P2 is equal to P2 naught into Chi2, where P2 naught represents vapor pressure of the pure component 2. According to Dalton's law of partial pressure, we can write the total pressure, that is P total, over the solution phase in the container as sum of the partial pressures of the components of the solution. That is, we can write P total is equal to P1 plus P2. If we substitute the values of P1 and P2 from Raoult's law into the equation obtained from Dalton's law, we get P total is equal to Chi1 P1 naught plus Chi2 P2 naught. Now we will write the mole fraction of component 1 in terms of component 2. So P total will be equal to 1 minus Chi2 into P1 naught plus Chi2 into P2 naught. Now you might ask, can't we write Chi2 as 1 minus Chi1? Of course you can write it. After simplifying, we get P total is equal to P1 naught plus P2 naught minus P1 naught into Chi2. What you can tell about the relationship between total pressure, partial pressures of pure components and mole fraction of component by looking into this expression. Try to figure out what information does this equation give. So, we can tell that equation relates total vapor pressure over the solution to the mole fraction of any one component. Secondly, the equation tells us total vapor pressure over the solution varies linearly with the mole fraction of component 2. Third, we can also tell that depending on the vapor pressure of pure components 1 and 2, total vapor pressure over the solution can decrease or increase with the increase of mole fraction of component 2. If we plot a graph of P1 or P2 versus mole fractions Chi1 and Chi2 for a solution, we get a straight line graph as shown here. These lines 1 and 2 pass through the points for which Chi1 and Chi2 are equal to unity. Similarly, in the plot, line 3 of P total versus Chi2 is also linear. The minimum value of P total is P1 naught and the maximum value is P2 naught. Assuming that component 1 is less volatile than component 2, that is, P1 naught is less than P2 naught. Now, if we know partial pressures of the components, we can determine the composition of vapor phase in equilibrium with the solution. That is, if we want to know the mole fraction of the volatile components which has been converted to vapor phase above the solution. If Y1 and Y2 are the mole fractions of the components 1 and 2 in the vapor phase, we can make use of Dalton's law of partial pressure here. Y1 is equal to P1 divided by P total and Y2 is equal to P2 divided by P total. According to Raoult's law, the vapor pressure of a volatile component in a given solution is Pi is equal to Chi Pi naught. According to Henry's law, the partial pressure of gas in vapor phase is proportional to mole fraction of the gas in the solution. That is, P is equal to Kh into Chi. If we compare these two equations for Raoult's law and for Henry's law, we can see that the partial pressure of volatile component or gas is directly proportional to its mole fraction in solution. The difference we observe is only with respect to the proportionality constant Kh and P1 naught. KH differs from P1 naught. And when KH becomes equal to P1 naught, the mathematical expressions for Raoult's law as well as Henry's law becomes equal. So we can tell that Raoult's law is a special case of Henry's law. Now let us discuss about another important class of solutions. Solids dissolved in liquids. Can you think of a few examples for solids dissolved in liquid? Sodium chloride, glucose, urea and cane sugar in water, iodine and sulfur dissolved in carbon disulfides are a few examples. If we speak about the physical properties of these solutions, a few properties are quite different from those of pure solvents. For example, let us consider vapor pressure. Do you remember that what is vapor pressure? Liquid will be vaporized at a given temperature and these vapors will exert pressure on the liquid phase. And when there is an equilibrium between the vapor phase and liquid phase, the pressure exerted by the vapors of the liquid over the liquid phase is what we call as vapor pressure. From the image, you can see that we have pure solvent and the molecules are undergoing evaporation. Can you tell me which molecules are undergoing evaporation? It is the surface molecules that are undergoing evaporation. In a pure liquid, the entire surface is occupied by molecules of the liquid. Now, if we add a non-volatile solute to a solvent to give a solution, the vapor pressure in this case is dependent only on the solvent because we are adding a non-volatile solute. Now the question is whether vapor pressure of the solution at the given temperature will be same as that of pure solvent or not. Can you just think what happens to the vapor pressure? Will it increase? Will it decrease? Or will it remain same? The answer is the vapor pressure of the solution at a given temperature will be lower than the vapor pressure of the pure solvent at the same temperature. Why would the vapor pressure decrease? You know that the molecules present on the surface will undergo evaporation. In the solution, the surface has both solute and solvent molecules, isn't it? By this, the number of solvent molecules which are present in the surface becomes less. As a result, the number of solvent molecules escaping from the surface is correspondingly reduced. When less number of solvent molecules undergoes evaporation, obviously the vapor pressure also reduced. And this is how you can explain the decrease in the vapor pressure of pure solvent when we add non-volatile solute. Now, suddenly you will think, how much decrease would be observed in the vapor pressure of a pure solvent when we add a non-volatile solute? This decrease in the vapor pressure of solvent depends on the quantity of non-volatile solute which are present in the solution, and this does not depend on the nature of the solute particles which are added. Example for this is the decrease in vapor pressure of water by adding 1 mole of sucrose to 1 kg of water is nearly similar to that of the decrease in vapor pressure produced by adding 1 mole of urea to the same quantity of water at the same temperature. We can use Raoult's law here. What does Raoult's law tell? Can you just state Raoult's law? For any solution, the partial pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, it is only the solvent molecules that are present in vapor phase, and they alone contribute to the vapor pressure. Let P1 be the vapor pressure of the solvent, Chi1 be its mole fraction, and P1 naught be its vapor pressure in the pure state. Then, according to Raoult's law, we can write P1 is directly proportional to Chi1. That is, vapor pressure of solvent is directly proportional to the mole fraction of the solvent itself. And we can write P1 is equal to Chi1 into P1 naught. The proportionality constant is equal to the vapor pressure of the pure solvent P1 naught. Now, if we plot a graph between vapor pressure and the mole fraction of the solvent, we will get a straight line passing through origin, that is, passing through 0. On the basis of Raoult's law, liquid and liquid solutions can be classified into two types, ideal solutions and non-ideal solutions. The solutions which obey Raoult's law over the entire range of concentrations are known as ideal solutions. These ideal solutions have two other important properties. One, the enthalpy of mixing of pure components to form the solution is 0. And second, the volume of mixing is also 0. That is, delta H of mixing is equal to 0 and delta V of mixing is equal to 0. What do we understand by telling delta H of mixing is equal to 0 and delta V of mixing is equal to 0? It means that no heat is absorbed or evolved when the components are mixed together. Also, the volume of solution would be equal to the sum of volume of the two components. Now, let us try to understand the ideal behavior of the solutions at molecular level by considering two components A and B. In pure component A, the intermolecular attractive interactions will be of the type AA, and in pure component B, the intermolecular attractive interactions will be of the type BB. Whereas in the binary solution of A and B, in addition to AA and BB type of interactions, we also see AB type of interactions. If the intermolecular attractive forces between AA and BB are nearly equal to those between AB type interactions, this leads to the formation of ideal solution. For example, if I speak of an ideal student, he or she should be obedient, punctual and honest, should always be focused on his or her studies, should be completing all the works in time, etc., etc. But do we find such a student with all these characteristics fulfilled? A perfectly ideal student is rare, isn't it? In the same way, a perfectly ideal solution is rare. But some solutions are nearly ideal in behavior. Solution of N-hexane and N-heptane, bromoethane and chloroethane, benzene and toluene, etc. are the examples to this category. Ideal solutions are the ones which obey Raoult's law over the entire range of concentrations, isn't it? So what are non-ideal solutions? Exactly, when a solution does not obey Raoult's law over the entire range of concentration, then it is called non-ideal solution. The vapor pressure of a non-ideal solution is either higher or lower than that predicted by Raoult's law. If the vapor pressure is higher, the solution exhibits positive deviation. And if the vapor pressure is lower than the expected from Raoult's law, the solution exhibits negative deviation from Raoult's law. The plots of vapor pressure as a function of mole fractions for positive and negative deviation from Raoult's law are shown in the figure here. The first graph represents a solution that shows positive deviation from Raoult's law. And the second graph represents a solution that shows negative deviation from Raoult's law. In both of these graphs, the dotted lines represents the vapor pressure that is predicted by Raoult's law, and the complete lines represents the vapor pressures exhibited by the solutions and the components present in it. Now the question is, when will a non-ideal solution have vapor pressure higher than that predicted by Raoult's law? And when will a non-ideal solution have vapor pressure lower than that predicted by Raoult's law? Thinking? You know that. You know the answer for this question. What is that? The cause for these deviations lies in the nature of interactions at the molecular level. In case of positive deviation from Raoult's law, AB interactions are weaker than those of AA or BB interactions. That is, in this case, the intermolecular attractive forces between solute-solvent molecules are weaker than those between solute-solute and solvent-solvent molecules. This means that in such solutions, the molecules of A or B will easily escape compared to its pure state. This will increase the vapor pressure and results in positive deviation. Mixtures of ethanol and acetone show positive deviation. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between those of the alcohol molecules and break some of the hydrogen bonds present between the alcohol molecules. Due to the weakening of interactions, the solution shows positive deviation from Raoult's law. Another example is a solution formed by adding carbon disulfide to acetone. The dipolar interactions between solute-solvent molecules are weaker than the respective interactions among the solute-solute and solvent-solvent molecules. So this solution also shows positive deviation from Raoult's law. Now coming to the case of negative deviations. The intermolecular attractive forces between AA and BB are weaker than those between AB. This leads to decrease in vapor pressure resulting in negative deviations. An example of this type is a mixture of phenol and aniline. Here, the intermolecular hydrogen bonding between phenolic proton and lone pair of nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between phenol-phenol and aniline-aniline. Another example is a mixture of chloroform and acetone. It forms a solution with negative deviation from Raoult's law. This is because chloroform molecules are able to form hydrogen bond with acetone molecule as shown in the figure. This hydrogen bonding between acetone and chloroform decreases the escaping tendency of molecules for each component in the solution, and as a result the vapor pressure decreases resulting in negative deviation from Raoult's law. Non-ideal solutions exhibit positive or negative deviation from Raoult's law. The solution which shows a large positive deviation from Raoult's law are also called minimum boiling azeotrope. The solutions that show large negative deviations from Raoult's law are also called maximum boiling azeotrope. What are these azeotropes? What is minimum boiling azeotrope? What is maximum boiling azeotrope? Azeotropes are binary mixtures having the same composition in liquid and vapor phase, and also they boil at a constant temperature. We cannot separate the components of an azeotrope by fractional distillation. We have two types of azeotropes called minimum boiling azeotrope and maximum boiling azeotrope. The solutions which show a large positive deviation from Raoult's law form minimum boiling azeotrope at a specific composition. Why the name is minimum boiling azeotrope? It is because when we plot constant pressure phase diagram for such a mixture, its temperature goes through a minimum. So it is called minimum boiling azeotrope. On the other hand, in the constant pressure phase diagram of maximum boiling azeotrope, temperature goes through a maximum. As told earlier, the solutions which shows a large negative deviation from Raoult's law form maximum boiling azeotrope at a specific composition.